Okay, so we are going to continue with the quantitative focus on representing solutions. And the last thing that we're going to do, the last formula we're going to do today, is really what you were going to use moving forward, and especially in grade 12 as well. So concentration, and again, your persnickety textbook sometimes will use the term amount concentration or percent concentration, which you're going to see in a second. So their wording is sometimes a little bit weird. If you're the kind of person who likes to Google and look for other videos, it can be a little bit strange. So just like this morning when we did solubility curves, we went where we did grams in 100 milliliters. Now we're going to look at a different way to represent quantity of a solute. So we are going to represent the concentration in terms of how much solute there is per quantity of solution. So the ones that we're going to start with are ones that you can buy solutions in the drugstore, the pharmacy, like rubbing alcohol or acetone, hydrogen peroxide, even vinegar is listed usually as a percentage because percents are easy for people to understand. In chemistry, we want to be able to compare substances to each other. So the last lesson in this chapter is applying stoichiometry to solutions. Okay, so what do we need to do stoichiometry? We need moles. So I'll talk about the different kinds of percentage values that are easy to understand, but then we will end with looking at molar concentration, or how many moles per liter, because that's more useful for us as chemists. When you have a concentrated solution, that means there are many particles of solute per quantity of solution. And then if something is dilute, then there's relatively few particles. Sometimes you can think of it, if it's dissolved in water, that there is more water than there is, a lot more water than there is solute. And if you continue and take biology, you'll even talk about different kinds of solutions related to what's happening in cells, hypertonic, hypotonic, isotonic. So this idea of if something is concentrated or dilute is important. This is in the booklet from this morning. Okay, so percent concentration is the simplest. We're used to dealing with percentages. The bottom of the fraction has to be bigger than the top so that you get a number less than 100. And even though it looks like there are lots of formulas, it's the same thing. And the question is usually really, really specific. So when you buy rubbing alcohol, it will actually say on it usually 70 or 90% VV, which means volume. So it gives you a clue about what you're doing. A mass volume percent is mass over volume. Volume is volume over volume. Mass is mass over mass. And it actually doesn't really matter which formula you use because they're all the same thing. The solution is in the bottom. So the bigger number, how much do we want to end up with? And then how much we're trying to dissolve, whether it's a liquid or a solid, goes in the top. And of course, times 100 because it is a percentage. When you have, on the sheet here, it says grams and milliliters. So if it's a quiz or a test, that's what I will give you. Your textbook might use kilograms and liters. They also go together. So we talked about grams and milliliters going together this morning. If you have to convert, so kilograms divided by, multiply by 1,000 is grams. So there are questions for sure that your textbook will give you in kilograms, but I won't do that. They might give you milligrams, and then you divide by 1,000 to get to grams. In this concentration percentage here, grams and milliliters can go together, so you often don't need to convert between milliliters and liters. You can leave it in milliliters. However, eventually we are going to change things into liters. And that is something that I am going to expect you to know, okay? And maybe you already do, but just, pick a nice color, make a box around it or something. So these percentage formulas, even though they're virtually identical, solute solution, solute solution, solute solution, they are on the formula sheet you get for like quiz, test, exam, whatever, okay? So if you are interested in seeing what it looks like and you're at home, go on Unit 4 and then it's the first file, okay? Not even in a submodule, like above them. So a pharmacist adds distilled water to 4 grams of a powdered drug. The final volume of the solution is 5 milliliters. What is the percent MV of the solution? So it tells you, put the mass at the top and the volume at the bottom, okay? And you might think, well, that's ridiculous, that's so easy. Yes, it is, okay? So again, the percentage, these are things that anybody can buy at the drugstore or whatever. So they need to be easily understood, right? If we say something is 90% rubbing alcohol or whatever, then people will understand 90%. That's a lot. That's really close to 100. And that's what we want. We want people to know that solution is very concentrated. That solution is not very concentrated. So even if you forget that it's solute over solution, you could do mass and over volume. That would work here. You could forget about the mass and volume and just write solute over solution. That would work here. Percentage is times 100. So, and you would already know that, okay? So try not to push out of your brain things you already know. So we have 4 grams of the powder we're trying to dissolve in water to make 5 milliliters of a solution. So 4 divided by 5 times 100 is 80. You can think of the logic of your answer, 4 and 5. 4 is almost 5 out of 5, right? So should it be pretty close to 100? Yes, it should. That's a pretty high percentage. This is a pretty concentrated solution. There are questions where maybe you have to solve for the top or you have to solve for the bottom. So that does involve a tiny bit more math or a little bit more algebra. So you can continue what we did before and use inverse operations if you want to make sure you get that math right. So rubbing alcohol is commonly used as an antiseptic for small cuts. It is sold as a 70% VV. So again, it's telling you volume. Solution of isopropyl alcohol in water. What volume of isopropyl alcohol is used to make the final solution? So it tells us percent VV. times 100. We are given the percentage this time. So 70%. We're trying to find the volume that's going to be dissolved in 500. So now you have some options. Some of you, again, who enjoy math or who take a lot of math, then you might have changed this into 0.7 without really realizing what you're doing. But you can just follow like inverse operations. If you're multiplying by 100, how do you, what do you have to do to get rid of it? You have to divide. And then the 500's in the bottom, or divide. What's the inverse of that? It's multiply. So 500 times 0.7 is 350. With these percentage ones, you might have even thought to yourself, aren't we just finding what 70% of 500 is? Basically, yes, that's what you're doing. So with the percent calculations, they are on purpose meant to be very, very straightforward. Again, so that if somebody is at the drugstore trying to buy rubbing alcohol, they understand that 70% is reasonably concentrated versus like 5% or 10%. Okay, so the next ratio of solute to solution calculation we can do is parts per million and parts per billion. So we use parts per million, or ppm, and parts per billion, ppb, when you're trying to find usually quantities in the human body or the environment. So if you think about inside your body, generally speaking, you wouldn't want a lot of something. Same thing with the environment. If you are an environmentally conscious person, you follow the news, they often express the amount of carbon dioxide in the atmosphere acting as a greenhouse gas in parts per million. Do we want a lot of carbon dioxide in the atmosphere? No, but they're measuring, and they usually report and make graphs with how the parts per million. And we look at the trends and when else was there spikes and ice ages and all that kind of stuff. The example we're going to do talks about a fungus on a shipment of cashews that is toxic. So if something is toxic, then you would also want the amount to be very small. When you have a water bottle, it's got a label. It talks about, this is not very hard water. Sometimes it'll list, Tucker, yours will. Oh, they totally changed it. Oh no, here. Parts per million. How much bicarbonate, how much calcium. Not those substances are toxic, but you want to know in a tiny amount how many ions are in there. Okay? So it's still solute over solution, but instead of times 100, it's times 1,000,000 or times 1,000,000,000. If you don't prefer scientific notation, you can use 1,000,000, which is 6 zeros. That's why it's 10 to the power of 6, and a billion is 9. And that's why it's 10 to the power of 9. That'll work too. But it's still the same thing, solute over solution. Usually grams and milliliters, we're usually just talking about water. Even inside the human body, we are mostly water. 70% of our cells, our makeup is water. So like this morning, grams and milliliters of water are the same thing. You can use them interchangeably. So a fungus that grows on cashews produces a deadly toxin. Any shipment of cashews contains more than 25 parts per billion of this fungus is rejected. A company receives 20 tons of cashews. What is the maximum mass in grams of fungus allowed? Even this question, you might be saying to yourself, why is any toxin allowed? So maybe one day that'll be your job. You'll work in a quality assurance kind of way and say, okay, this is as much as we can tolerate. This is as much as we should put in the environment. Seems like a sort of a weird thing to do, but I guess, can we have 0 for everything? That's tough. However, there are substances that you should have 0. If you live in a place that has a septic tank or a well, and you take your water to get tested, even city water cannot have any bacteria that are called coliforms, which is E. coli, because that's very deadly. So that has to be 0. So there are cases where the amount of something in water has to be 0. But sometimes, there's a little bit. In a question like this, logically, if you're going to do especially parts per billion, then that's like 1 part in a billion parts. Then the answer we should get should not be too big, okay? So if you mess up your scientific notation or you're dividing and you get a really big number, then, that's your clue. Whoops, maybe I should go back and check my math, okay? The good news with parts per million and parts per billion, the unit is parts per million and parts per billion. So again, you're going to know what formula to use, and the formula is on the formula sheet. So again, either use 10 to the power of 9, or you can do a 1 with 9 zeros. That's a billion. It does give you 20 tons. That is a weird measurement. So in a question like this, I would probably give you the equivalency. So 1 metric ton, anyways. One ton is 1,000,000 grams. So again, either write out 1,000,000 or you can write it like this. So what I'm going to do for 20 tons, then I'm going to say that's 20 million grams. So I'm going to cheat a little bit with my scientific notation. We're only going to do one example for ppm and ppb, but it's the same sort of thing. You're either solving for the top or the bottom of the fraction, or you're solving for the parts per billion or parts per million. So in this case, we're given the parts per billion. We're looking for how much fungus can be dissolved on 20 million grams of cashews. And then because it's billion, you multiply by 1,000,000,000. So you can follow the same thing that you did before. Maybe your brain, actually I'll do this one this way. Maybe your brain wants to get rid of this first. So you do this times this. Maybe you can see that. You can do it that way too. Or maybe you want to get rid of the 10 to the power of 9. Doesn't matter. 7 zeros and then 25. Okay, and then we got to get rid of the 20 times 10 to the power of 6, or 20 million, which is now dividing, so we're going to multiply. So we have been using scientific notation. So however you chose to do that in your calculator, do the same thing. Use your EXP button, or you can put this number in brackets, that's fine. And you should get the final answer is 0.5 grams. So a small amount, which makes sense. Why would you want a toxin that's deadly in a big amount on the food that's going to be ingested? You do not. Okay, so parts per million, parts per billion, percentages, stuff you're going to put on the body, in the water, in the environment. Those units are fine. But when we're talking about chemistry in the lab and we're going to relate, trying to find like how much reactant is used, how much product is produced, you can do the same thing with solutions. However, you need to have the concentration in moles. So today, all we're going to do is look at concentration, moles, and volume. Tomorrow, we'll look at, what happens if you have a solid and you dissolve it and you want a concentration. So we'll kind of do what we did last unit and this unit together. Okay? So get out your highlighter, okay? This is a very important formula. So in the last unit I said in grade 11, changing grams into moles was a easy first step to get part marks. Moving forward, and when we get to grade 12, changing moles into concentration will be what I encourage you to do, at least that much to get part marks in grade 12. So again, your textbook is a little bit weird with its terminology. It might say amount concentration, just like it did sometimes with the amount in moles. It just said amount. Most of the time, you're going to see molar concentration or molarity or even simply molar. Okay? So the molarity is, or the molar concentration, amount concentration, is the number of moles of solute dissolved in specifically a liter of solution. So it is important here, you can see how many stars there are. That volume is in liters. So even if you wrote it down on the other slide, write it down here. Sometimes even if I have a little bit of, I want something to work out perfectly to a nice round number of marks, I'll make changing milliliters into liters worth a mark, okay? This is a very common first step in a question, okay? So all you have to do is divide. If you've done a lot with unit analysis and you think about it like decimal places, moving the decimal 3 spots, that's the same thing as dividing by 1,000. That's the beauty of the metric system, so that'll work too, okay? So the unit for molarity or molar concentration, or just concentration, is moles per liter. In grade 11, I really try to just use moles per liter. I believe your textbook does the same. Once we switch to grade 12, chemists are lazy and we often just use capital M, but both of them will work. The nice thing about the concentration unit, as when it's written like this, moles per or divide by liters, that tells you what the formula is. Moles divide liters. Okay? So it will hopefully remind you that in this case, the volume has to be liters, hopefully. So again, when somebody comes to me and says, I need a solution to do a reaction and make a precipitate, I need a solution to test the pH of it. So you probably did a whole bunch of pHs in grade 10. You used litmus paper, you probably did Sprite, maybe dish soap, all that kind of stuff, and some solutions like acids and bases. I have to say, what concentration do you want it to be? So if you've ever looked at a stock bottle and seen a number and then the letter M, then that is the concentration of that solution. So 1.5 molar solution of hydrochloric acid, that tells you something about that solution. So the acid inside of our stomach is 6 molar. So if you think about, that's very concentrated. If you throw up, that it literally burns. Why is it burning? Because acid is burning your esophagus. If you unfortunately have misfunctioning parietal cells in your stomach and you're not making enough mucus and you get ulcers because the acid is eating away at your stomach lining. So 6 molar is a very concentrated acid. In grade 9 and 10, we usually use about 0.5. In grade 11, mostly 1. And then next year, there's one lab where we do rates of reaction where we'll use 3 and 6. But I have to tell you guys to be very, very careful because, and you'll see what we're going to do is test rates of reaction. And you guys are going to put a piece of magnesium in the 6 molar acid and try to time it. And it literally takes like 20 seconds for it to be totally dissolved. So the concentration is going to matter for how fast a reaction can go, which is next year, and all kinds of things. So this is a very, very important calculation. If you are into triangles, you can change it into a triangle. On the formula sheet, there are both forms, so you can certainly use whichever form you like, okay? The only unfortunate thing is the English letter C. Capital and little letters look virtually identical, and later on, when we do energy next year, we're going to use little c to mean something else. So try really hard to make your big C's look like capitals, okay? It'll save you later. I promise. And then, of course, N is the number of moles, exactly the same as last unit. You can write out the word MOLES, or if you're a lazy chemist, you can write MOL, okay? So today's homework is just simple examples like this one. A sample of laboratory ammonia solution has a molar concentration of 14.8 moles per liter. What amount in moles is present in a 1.5 liter bottle? So it's already in liters. Isn't that nice? This question would be out of like 2 marks. Really, really simple. So then the more marks something is worth, then that probably means the more math you have to do, just like the last unit. So you can do the same thing if you're like an inverse operation person or a triangle person. You can rearrange the formula with numbers in it or with the letters first. So what I'll do is I'll split my paper and do both. You guys have a huge spot there. So you can, if you like the triangle way and you want to just write down that or whatever, it's up to you. So concentration is moles over volume. So I want moles by itself. That's the unknown. Here I'm dividing. How do I get it by itself? The inverse is multiplying. You have to multiply on both sides. This cancels. You get 22.2, 1.5 times 14.8. The liters cancel, and you're left with moles. I'll also do it with triangle. So moles is C times V. Okay, so the homework, I've tried to list it as, or I divided it by topic. So don't just do, like these are obviously important, but don't forget to practice these as well. If you want it to all be mixed together, you can do some of the last ones. But remember, you do get a formula sheet, you do get the formulas, so that can help you, especially with the percent ones and the ppm and ppb, because they look almost the same, okay?